Appreciate that introduction. Thank you. Yeah, I guess I could just get right into it. So I work for Entrust Engineering, which was previously EN Engineering. We have like 3,100 members throughout 26 states throughout the United States. And we mostly deal with oil and gas transmission as well as high-pressure pipelines. So my experience working with probabilistic models and Entrust Data Solutions team have partnered with a utility operator group to develop and incorporate a comprehensive predictive machine learning modeling solution in order to verify specific at-risk assets that are on their transmission natural gas distribution system. This presentation will discuss the customized machine learning solution, modeling solution, including how the solution will be used to identify the potential likelihood of an asset being of a certain risk type, as well as what is needed to create a predictive model and what type of data and GIS utilization we use for this case study. So the foundation of this analysis focuses on the utilization of GIS data in conjunction with advanced analytics, in this case, predictive analysis, to identify assets for a client. And when most of us think of predictive analytics, or at least when I think of predictive analytics, we need a lot of data to be able to make these predictions. And then this idea of predictive analytics requires GIS data and large amounts of data in conjunction with each other. So these predictive analytics shines when there's a lot of data to look at, and as the data sets expand in size in like rows, columns, just all types of data, using this extra information to come to more accurate results. These accurate results are, of course, based on the underlying quality of the data. So without good quality data, there's not a lot of predictions that can be made. So using the large amounts of GIS data, but even so, information capture is not always perfect. So some questions can't simply be answered when information is left out of data sets, and predictive analytics bridges that gap. It uses the large amounts of data with the unknown data to make predictions on the things that are missing from the data sets. So now we'll get into the actual case study where Entrust and myself were able to utilize GIS and predictive analytics to help a client assess their pipelines and their risky assets. So we were approached by a client that had previously installed many different type of assets on their natural gas distribution systems, and a certain portion of these assets were that they had already installed had been deemed defective, and they had to go into all these different locations and extract them and install new assets, and this posed a risk to their system, and therefore they needed to all be phased out and replaced. So what was the client's main issue that necessitated a third-party solution? The record keeping on these assets was not very good. We're all familiar with that, where data is incomplete, missing records. There were many types of assets that were installed over a long period of time, and the client had little or incomplete information or knowledge on where these assets were in their system. So initially, the solution that the client initially used was looking at the records and using their SME knowledge, and they were able to locate some of the defective assets within their system. But with only a certain understanding of the conditions that affected where these certain at-risk assets were, they were not able to accurately find the assets on their system when excavating. So the cost of continuing to dig up certain assets in random locations without high accuracy became too much of a cost, and they believed that continuing to excavate would be just too costly and risky. So they came to us for a machine learning solution, specifically the predictive analytic solution, with the goal of just locating the remaining assets that they have not located with higher accuracy to mitigate risk and reduce costs. So now I'll talk a little bit about the necessary steps to creating the predictive model. That a lot's been talked about in the previous presentations. The initial steps in producing a predictive model is understanding the initial raw data sets and will be used. The data provided by the client contained many attributes associated with GIS. This GIS data is all the client's data already possessed on their system. So information like spatial data, along with where they're located, the data that encompass the physical features of the assets, as well as pipe segments around the locations, and as well as time information of when the assets were installed, and things like that. And after taking a deep dive into the raw data set and getting a full understanding of everything that is represented with the data, we can then use our understanding to make improvements to the data set so that it performs better when used in an analytical model. In some cases, the improvements come from outside data sources, not just data that's already present in their systems. And for this specific case study, we spoke with client subject matter experts to come to the conclusion that there were multiple parameters that affected where these assets were located, but alongside that, there was weather parameters, specifically the amount of rainfall per day. So what the clients found was that when there's more rainfall per day, the specific asset that was put into the ground was actually a more risky asset. So we use this SME knowledge to further enhance the data set, including to include weather data, and we spatially join this weather data with where the assets were to then use we use NOAA, the NOAA weather stations. And the client's operating cities had unique weather stations that could be used to gather the weather information for each asset. And we spatially joined that to allow an increased data set. This has also been talked about in previous presentations where, of course, the information is not always complete. Record keeping is not always perfect. And these errors are things we've all seen, like white space errors, nulls, punctuation, even like letter case errors, just to name a few. So this portion of model training is called feature engineering, and it's really what was actually talked about in the previous presentation. We use pandas in Python just to clean the data set, correct any errors. And as stated, the better the data set is scrubbed of the errors, the better the machine model will perform. And yeah, these tables just show a couple examples of how this is corrected. So all these diameters are really 30 inches in our eyes, but then we want to make it as readable as possible for just an analytical model, so we make them all 30. And similar with installation dates, we want to parse out the separate information for each year, maybe even month and day. So we separate those out. These are just a few examples of ways you can feature engineer data sets to improve the quality and then overall produce the predictive capabilities of a model. And yeah, this step is actually pretty time consuming when looking at machine learning. It's just a crucial step, so we really dive deep into the data, get to know it, and make any improvements we think would help improve the model. So now we'll get into the actual model development. So predictive analytics can take many forms, and what I mean is there's many different types or approaches that can be used to predict accurately. And each case is unique, and it really depends on the type of data you have, as different analytical techniques produce different results. And it's our job as analysts to just determine which model will produce the best results for each data set. And this is just done by testing a bunch of different models. And given the scope of work and the characteristics of this specific data set provided by the client, Entrust decided to utilize a machine learning decision tree random forest model. And machine learning really is like just a broad term that encompasses many types of models that can be used. And after testing the multiple different models, we did come to the decision to use the random forest model. So what is the random forest model? The image in the slide is pretty helpful in understanding what actually a random forest model is. And what you're seeing is just actually a subsection of a random forest, which is the decision tree. And each box is made up of an attribute and that is associated with one asset. And as you follow the boxes downward towards the bottom, they branch off, hence the name decision tree. And they branch off into different directions based on their attributes. And they just make up, as the branches continue downward their path until eventually they reach the end, which then is the full asset description outlining all its asset attributes. And then, as I said, this image is just a small section of the overall random forest. Showing the full thing would definitely just take up too much space. There's thousands of decision trees that make up the random forest. And as the forest grows, the prediction powers become increased, as it's just looking at thousands of the decision trees and compiling the results to come to the random forest overall predictions. So I'll get into the actual model performance now. So as I previously stated, Entrust and we were brought in to support a client due to incomplete record keeping and the low accuracy of the client's data on their risky assets. And the client had already excavated the thousands of assets and this is helpful in creating a diverse group of assets that have already been looked at, so we know the characteristics of all these assets and whether or not they are risky or not. So the predictive model will utilize the known asset records that were identified by the client to make the predictions on the unknown assets. This is referred to as model training, and we're using training data. So using the thousands of records that already contained the desired outcome of the asset type, or the risk asset type, the outcome can be derived from the model. And each asset is defined by its attributes, and the model recognizes these defining qualities and determines which attributes are more closely associated with the desired asset type that will be needed to be removed from their natural gas distribution system. So once the model has been trained to fully understand the data set or understanding the patterns associated with the outcomes of the defective assets, it can then be tested to determine how accurate it can be used when used on the real data set, not just the data set where the assets are already known. And this is actually probably the most important step in training a predictive model, because the type of asset may be known to us, but to the model, it does not know the asset type yet, which allows us to derive the performance of the model because the performance of the model is making a prediction on what the asset type is, while we already know what the asset, if it's risky or not, is. So we can then look at the outcomes of the predictions and know its precision, sensitivity, and accuracy scores. And I do give a brief definition of each one. They're pretty similar. Precision is how many of the assets are predicted correctly, with the word target in the table meaning defective assets. Precision is how many of the assets are predicted correctly, and sensitivity is just the proportion of defective assets that the model was able to identify. And overall, we found that while using the random forest model, the predictions were highly accurate, so we were able to not just use the testing, we performed the full analysis with their full data set. So yeah, once the model has been trained and tested using a subset of the overall data set, the model is ready to be used on the remaining assets that have not been excavated by the client to determine the remaining assets and their risk profiles. This gives us then the model results. So the model was fed the remaining assets, and using its trained understanding of the assets and their characteristics, the model produced a prediction asset type for all remaining assets, and the predictive asset type would fall into a category of a defective asset or not. And the graph shown is just a histogram that shows the overall results for the whole analysis. The x-axis is the confidence score, or more intuitively, just the model's confidence that a particular asset is a defective asset. And since the goal for the client and the model was to determine instances where defective assets needed to be replaced, the blue portion on the right shows, or on the top shows when the model was more confident the asset was defective and needed to be replaced. We use the histogram because it just quickly shows the overall distribution, and from the distribution we can make some quick inferences. For example, from this graph, most of the remaining unexcavated assets are anticipated to be non-target or non-risky Ts or assets, and there can be many factors that led to this result, but the most influential One is that the client had already started this work a long time ago. So many of the assets they found had already been excavated and deemed not risky. And we had to find the remaining risky assets, although they made up a small portion of what remained on their system. So on the last slide, I showed just an overall view of the model predictions. These 6 graphs are showing a more refined view of the overall histogram by showing different regions within the client's operating system. And you can see by their distributions that there are some locations where many more assets are deemed at risk and will need to be replaced when compared to other locations. In particular, the middle right and the bottom left, the overall riskiness of those locations remains high, while you can see in the other graphs, relatively there's fewer risky assets within this group. So from these graphs, what I'm trying to illustrate is that although the client was progressing towards finding the remaining risky assets, a machine learning solution allowed them to hopefully identify more quickly where the remaining assets were on their system more efficiently than if they were to just continue digging, only using the certain knowledge that they had. So with the low amount of defective assets that were left to be found, the at-risk assets became harder to locate, and therefore higher accuracy to find them was more needed. So overall, what really was this project about that we sent to our client? Our client had incomplete records of something of vital importance, risky assets, that without excavation would cause potential damages to their system and even just health risks to all over their operating systems. So these risky assets needed to be addressed quickly and accurately, and they came to us to create a solution for that. And after understanding the makeup of their GIS data that they had, and with the addition of external data and the help of their client SMEs, we utilized this advanced technique or analytical technique to develop a predictive model for them that would aid in addressing their needs of locating the remaining Ts on their assets. So in this case, for this specific case study, the machine learning solution correctly helped a client minimize risk. The client using our solution was able to prioritize the most likely candidates for removal, thus minimizing the amount of time these problem assets remained on their system. This case study is just one of the many examples of ways advanced analytics can support our clients' needs. As well as risk mitigation, many operators must properly maintain their assets over time. So machine learning can aid in tasks such as maintenance prioritization in a much similar way to the case study I've just outlined. A client can take their data and perform pattern recognition to identify not just risky assets, but any number of asset properties that need to be identified. So yeah, utilizing the abundance of data that GIS is able to provide, advanced analytics in this case was a useful tool that helped our client improve their operating systems. Thank you.
Do we have any questions?
So this was based off of rainfall data with the main variable, right, that you're talking about?
What was that?
The model was based off rainfall data?
It was all of the asset data, so all of the attributes were included in the model, but then when we talked with subject matter experts from their understanding of the assets, they realized that rainfall was a high predictor for the riskiness. Like when they dug into the ground, they found that rainfall was a high predictor of the asset being a risky asset. It wasn't the sole variable. Yeah.
What's the timeline that the project took, prepping the data and then kind of refining the model?
Yeah, so from start to finish, it was ongoing. So it took like 4 months for the initial review, and we sent that back to them. But then after that, we sent them the model results. So they dug some more, and they found more assets to give us. So then we refed the data into that. So it was an ongoing project of like 8 to 10 months total, but we gave them initial results like in 4 to 5 months, yeah.
Thanks.
When you were judging your model performance, did you use RMSE or ROC curves or anything like that? How would you come up with your, performance of your model when you were doing the precision of your accuracy?
Yeah, I'd have to get back to you on that. I don't remember it, like at the moment. I'd have to like look at our report and stuff.
There's no more questions? Thank you.
Yeah.